Hello. Okay, so let's get started. So hello everyone, my name is Hongliang Xu. I'm a software engineer on the streaming data team at Uber. So tonight I'm going to talk about uReplicator. It's our open source solution to replicate Kafka data between Kafka data centers. And it's first open sourced in June 2016, and now we have developed a second generation of the uReplicator called the Federated Replicator, and I'm going to talk about both of them tonight. So here's today's agenda. So first I'm going to talk about the use cases of the replication at Uber and the scale we want to support. And then I will talk about the motivation why we want to build our own uReplicator instead of using the open source mirror maker. Then I will go through the high-level design of both uReplicator and Federated uReplicator. And I will also talk about the issues we had and how we solved the issue. And at the end, I will talk about some future works. So first, this is how Kafka looks like at Uber. So in each data center, we have a regional Kafka cluster. And the applications will use a REST client to produce a message to the Kafka REST proxy cluster. And the REST proxy will forward the message to the regional cluster. And we also have one aggregate Kafka cluster in each data center. It has a full picture of all the regional clusters. And here we use the uReplicator to copy the data from regional cluster to the aggregate cluster. So today, Kafka at Uber is running at a very large scale. It's transporting over 1 trillion messages per day. That's over like petabytes per day. And we are also supporting tens of thousands of topics in all the clusters. So there are two major use cases for the replication at Uber. So the first one is for aggregation. It means copy the data from regional to aggregate cluster. There are two major purposes. So one is for all active. So the consumer can consume from aggregate cluster, so it can have the full picture of the data. And second is for ingestion. So our Hadoop pipeline will ingest the data from the aggregate cluster instead of from each regional Kafka cluster. And the second major use case is migration. So when a user wants to migrate a topic from cluster A to B, normally we'll set up a uReplicator to copy the data from B to A, so the producer can move first and the consumer can move whenever they want. Okay, so I'm going to talk about the motivation why we built uReplicator. So back in 2015, we were actually using the open source mirror maker, but we ran into several issues. The first is the expensive rebalance. The mirror maker is using the high-level consumer, so when we start the mirror maker or during the processing, sometimes it will trigger a rebalance. And if we have many topic partitions in that consumer group, then the rebalance time will be very long. I think we noticed 5 to 10 minutes rebalancing time, and during those periods of time, the mirror maker cluster is totally inactive, so we will have 10 minutes downtime. And second issue is the mirror maker is using a static topic list, so it's difficult to add topics. If we want to add a new topic, we need to update the whitelist list and restart the whole cluster. Then it will cause the first problem again. And third problem is it's just at that time the high-level consumer only support auto commit, so it can cause potential data loss. So the consumer might commit a message before we produce it to the destination. And the final problem is the metadata sync issue. So the whitelist, the file may not be synced on each node, so that will also cause some problem. So to solve this problem, we need to build a new replication solution, and we have some requirements for that. So first, we need stable replication. That means the rebalance should be very fast, and during the rebalance, the replication should continue, should not be stopped. And the second is we need a simple way to operate the cluster. So we need a simple way to add or delete topics, add or delete nodes, and with all those operations, we don't need to restart the whole cluster. Third is, of course, we need to support high throughput and should be able to scale with Uber's traffic. And the next requirement is we have to make sure there's no data loss during the replication. We also need an auditing system to monitor if there's any data loss occurred during the replication. So these are the requirements. So with these requirements, we came up the first version of uReplicator. So the uReplicator features a controller layer. We use Apache Helix as a controller because it's being proven to be very reliable and stable. And it can also persist the source of truth like topic partition assignment in Zookeeper. Also, the controller is responsible for handling adding and deleting topics. We can use the REST API to add or delete topics. And the second, the controller is responsible for handling node changes. It can, when we add or delete a node or a node goes down, it can handle the topic and the assignment. And the controller, so the controller is responsible for calculating the partition assignment and assign the partition to the workers. So this is a basic workflow of how controller works. So we have a REST API to post the data to tell the controller we want to whitelist one topic. So the controller will calculate the ideal state of the topic partition assignment inside the controller. So for example, here the partition 0 is being assigned to the worker 1. So with help of Helix, it will update the ideal state in Zookeeper. And in each worker node, there will be a Helix agent to get the notification of such assignment from Zookeeper. And after the Helix agent got the update, then we'll start processing the assignment in each worker. So here's the detailed look at each worker. So the Helix agent got the topic partition assignment, and they will forward the assignment to the fetch manager. And inside each fetch manager, there will be actually there will be only one fetch manager. So inside the fetch managers, there will be a leader finding thread, and the manager will find the leader broker for this partition, and it will dynamically start the fetcher thread to fetch the data from the leader broker. So the fetcher thread is just a simple consumer. It will fetch the message from the source broker and put it into a blocking queue. And in the worker thread, there will be a Kafka producer to get the data from the blocking queue and forward to the destination Kafka cluster. So one thing we want to avoid is data loss. So inside this process, we only commit the message after we flush the Kafka producer. So in this case, we can avoid data loss. So in case one worker node failed, the Helix controller will get such notification from the live instance node in the Zookeeper, and it will recalculate the ideal state and reassign the according topic partition to a new worker to make it keep running. So with this design, the uReplicator running production perfectly well until 2016. So at that time, we are doing a lot of failover tests, and we found the uReplicator cannot catch up the traffic in source brokers. So even the failover is over, it takes a long time to catch up the lags. So we did some tests. So we shut down the intermaker worker for 4 hours, and eventually it takes like 8 hours to catch up all the lags. So we definitely want to solve this issue. So first, we identify there are two phases during the catch-up period. So the first is the full speed phase. In this phase, all the workers are running at full speed, catching up lags. And the second phase, we call it long tail phase. So after the full speed phase, some of the workers become idle. They already caught up the lag, but some of the workers are still very busy. So let's solve the first problem. So in the full speed phase, we identify one issue as the destination Kafka brokers. The CPU usage is very high, and it's due to the request handler usage. We have too many incoming requests to the destination brokers. So one solution to resolve that is we increase the batch size so we can have a bigger batch, but less frequent requests. So we tune the producer configs to increase the batch size, and there's the linger time to accumulate a bigger batch. So the result is very good. So the average batch size increased like 5 times. And because of the bigger batch, the compression rate is also improved. And the second solution we found is for one-to-one partition mapping. So natively, the Kafka producer is using round robin to produce a message to all the brokers in destination. So if a topic has n partitions, then it will be assigned to n workers, and each worker will produce to n brokers in destination. So one topic will end up like n square connections. So with so many topics, it becomes a DOS attack to the destination Kafka cluster. So we introduced the one-to-one partition mapping. So we check the partition ID in source broker, and we produce it to the same partition ID in destination. So the connection in the destination cluster, the total connection will be bounded by the total number of partitions. With this, we can reduce the contention in destination brokers a lot. So with this improvement, so we improve the full speed phase throughput a lot. So almost double the throughput on each broker. And with this, we can like reduce the full speed phase time by 50%. So this is full speed phase. Then we still need to solve the long tail phase. So in this phase, some workers are busy, some workers are idle. Yeah, of course, we don't want the workers to be idle. So the first solution is we introduce a dynamic workload balance. So original partition assignment is only based on the number of partitions. It's like natively round robin to assign the partition to each worker. So each worker will have similar number of partitions. But some heavy partitions might end up some workers. That's why we have the long tail phase. So in the workload-based assignment, when a topic is added, we will first check the workload of the topic. So workload is defined as the byting rate in the source Kafka brokers, and we retrieve it from Chaperone 3. So by the way, Chaperone 3 is our auditing system. Auditing system to like monitor data loss, and I will talk about it later. And it can provide the workload information for uReplicator. So when a topic is whitelisted, the controller will check the workload for the topic, and also check the total workload on each worker, and will assign the partition to the worker with the lightest workload to balance the workload. And they will also do the rebalance periodically. So I think it's every 10 minutes, it will scan the total workload on each worker. And if it finds one worker with a much heavier workload, then it will move the heaviest partition to a lighter worker. And the second solution is lag feedback rebalance. So we have a thread to monitor the lags for each partition. Then we will convert the lag into workload. So we consider a larger lag is considered heavier workload. Then after we convert it to the workload, then we will use the first solution, the algorithm, to balance the workers. We also have some dedicated workers for lagging topics. So first, we will assign some lagging topics to dedicated workers. And those dedicated workers will run at full speed to catch up the lag for the lagging topics. So with this improvement, you can see in the left picture, every 10 minutes we run the rebalance, and the sum of the partition is moved from one worker to another. On the right picture, you can see at the red circle here. So at that time, some of the workers have already become idle, and some lagging partitions are still on one busy worker. So the rebalance distribute the lagging partitions to multiple workers, and all the workers can help to catch up all the lags. And we actually reduce the, you can see the yellow line, we reduce the long tail time a lot. So with these two improvements to improve the throughput, it runs fine. It runs fine for a while. We don't see lags, but unfortunately, we run into some other issues again. So this time, so first is scalability issue. So the Kafka cluster at Uber, the scale is increasing very fast. And the number of partitions in each cluster also increase a lot. So in the uReplicator, each deployment so one source to destination replication is handled by one deployment. So the Helix cluster, the Helix in that deployment is responsible for all the number of partitions, and it soon becomes a bottleneck. So for the biggest cluster, if we do a rolling restart of the mirror maker workers, it might take up to 1 hour to finish a full rebalance. So a straightforward way to solve this issue is to split the big pipeline into multiple smaller ones. But this will lead to the second issue. So we already have a lot of clusters at Uber and set up different replication pipelines between clusters. So we already have a huge number of deployments, and it takes a lot of engineering effort to maintain the pipelines. And if we split into multiple smaller ones, we will add more deployments. And also, it requires a lot of engineering effort to set up a new pipeline for new clusters. Also, we have a third issue. So we don't have a centralized place to do the sanity check. For example, the loop or double route. So one time we whitelist a topic from cluster A to B, but we also accidentally whitelist from B to A. So it becomes a loop. And so actually the topic has less than 10 QPS, but it ends up with 100K QPS. Also, we have the potential problem like double route. It means a topic can be replicated from A to B, but through two different passes. So to solve these three issues, we built a Federated Replicator. So before we go to each component, let's look at some high-level concept of Federated Replicator. So as I mentioned, in the old pipeline, one source to destination replication is handled by one deployment. That's why we end up with a lot of deployments. So in Federated Replicator, we group the same purpose deployments into one. For example, the replication pipelines, we group into one deployment group. So all the aggregation replication will be handled in this group. So the engineer doesn't need to deal with so many deployments. They only need to deal with a limited number of deployments. Also, in one deployment, we will have one manager to handle all the pipeline creation, adding topic, which requires human effort before. So in each pipeline, you can see there's a pipeline called route. So one route on the high level equals to one deployment in the old uReplicator. It contains one controller and a bunch of workers, and they are registered to one Helix cluster. The difference is in the Federated Replicator, the same source to destination replicator will be handled by multiple routes. So each route is kind of subset of the old deployment. So with these two concepts, we solve the operation overhead issue by limit the number of deployments. And the smaller route, we solve the scalability issue because each route is smaller, and we can configure to deal with only a limited number of partitions. So we have third problem, the sanity check. So we introduced a component called uReplicator front. So it's a single endpoint for end user or other services to do a whitelisting or blacklisting. So we still have the REST API for them to whitelist or delete topic. So in uReplicator front, it will persist all the existing whitelist in database. So when it receives a request to whitelist a topic, it will first retrieve the information from database for that topic, and then check with the new request, new whitelist, will it result in a loop or result in a double route or other rules. If it passes the sanity check, then the front will use the source to destination requirement to find which deployment group it belongs to, and will forward the message to the manager in that deployment group. So the uReplicator manager is responsible for creating new route and assign the topics to the route. So here's the detailed process, how it works. So when the manager receives the request, it will first check if there's already a route existing from the requested source to destination replication. If it doesn't exist, then it will choose one controller and a bunch of workers from the pool inside each deployment, and tell them to join one Helix cluster. And after they join one Helix cluster, the controller and the worker basically becomes the old uReplicator pipeline. And after that, the manager will assign the topic to the route, and they will start replicating. And if there's already some route existing for that source to destination replication, then the manager will check each of the existing routes. So we set up a rule. So each route will have a maximum number of partitions. So the manager will compare the existing number of partitions in each route, and will check if the new topic can fit into the route. If it can fit, then we just added the topic to the smallest route. And if all the route cannot fit the new topic, then we will create a new route. So let's look at the controller and the worker. So it's basically the same thing. From the function level, it's the same as the old uReplicator, but the difference is in the old deployment, when we use a config file to tell them which Helix cluster it belongs to. So when they started, they directly know which Helix cluster they should join. but in the Federated Replicator, they are all in standby mode when they started. They need the uReplicator manager to tell them which Helix cluster you need to join. So we also use, so when they started, they are in standby mode and listening to the manager. So for the communication between manager and the controller worker, we still use Helix. The reason is we have the same reason we can persist the source of truth route assignment and the topic assignment in Zookeeper instead of like recalculating everything. So there are two steps for the controller and the workers. So when they first started, they're in standby mode and listening to the manager, and the manager will calculate the route assignment in previous slides and tells each controller which route and which route ID you should join. So the controller and the worker will join to that Helix cluster. And after that, the manager will still use the same protocol to tell the controller you are responsible for this topic. And we have some special design for the Helix Helix communication strategy, like in the resource and the partition. So we have some special way to distinguish if it's a route assignment or it's a topic assignment. Okay, so we also did some improvements to the Federated Replicator since we don't want to run into some performance issues very soon again. So we have the Federated Replicator has a feature called auto scaling. So as you remember, each route is created based on the number of partitions. So after it's created, the manager will scan the total workload in each route and also checks the total lag in each route and convert it to like total workload. And then we want each worker to have an expected workload on each worker. So for example, we want each worker to handle like 10 megabytes per second traffic. Then we use the total workload to divide the number and calculate how many workers we actually needed in this route. So if it's larger than the existing workers, then we'll dynamically add more workers from the pool to this new route. So we can automatically scale up the route to resolve like workload issue or lagging issue. And the good thing is if the workload goes down or the lag is resolved, we can calculate the new number of workers and release the extra workers to a smaller number. Okay, yeah, that's how pretty much the Federated Replicator works. So we still have one last requirement for auditing. So we have a service called Chaperone. It's an auditing service. Basically, it consumes a message from all the Kafka clusters and compare the message count for each tier. Then we can tell if there's any data loss during the replication. It's also an open source project, and here's a link to the blog and the GitHub link. So finally, let me talk about some future work. So first, we want to keep improving the open source project. So first, the Federated Replicator is currently in a separate branch. We are already running in production, but it's already still in a separate branch. We want to merge it back to master. The new uReplicator will support both federated mode and the non-federated mode. You can just use the flag to specify that. And second, we want to make the uReplicator extensible framework. So currently it's more like already support like from Kafka to anything, and we're investigating if we can like make a framework like from anything to anything. So this is the link to the blog and the GitHub. Yeah, that's all. Thank you. So any questions? Okay, so let me repeat the question. So how to compare it to the Kafka Replicator? So I think the Kafka Replicator, I'm not familiar with the detail because it's also pretty new, and they only have the doc. They didn't open source it, so I don't know the details. But for the federated uReplicator, the difference is we can like set up the deployments automatically, so resolve a lot of manual effort. Okay, yeah.
But when you are running, it's possible that for this topic, sorry. So it's like, for example, a given topic probably in this time is really heavy loaded, but next second it becomes idle.
Yes, that's true. So that's why we do the rebalance every 10 minutes, and we retrieve the workload every 10 minutes. So it will be like scale up, scale down according to the workload.
Was the lag still observed when you increase the number of workers equal to the number of partitions you had? Did you still observe that?
You mean to resolve the lag?
Yeah, like you see the tailing lag, right? So certain partitions and workers are under heavy load, rest of them get completed.
Oh, yes.
Did you still see that when the worker count was equal to the number of partitions?
Can you repeat again? So yeah.
So if worker count is equal to the number of partitions,
okay.
Did you still see the problem?
We normally, so in our use cases, we never saw that because the largest, so we always have like multiple partitions on each worker. So, yeah, I actually understand your question. So normally when we spread the partitions to multiple workers, it will resolve the lag. Actually, it will help to resolve the lag. So in the past, when we have like lagging issue, and if it's like the number of partition is smaller than the number of workers, the best way to resolve that is to expand the number of partitions and spread to more workers.
So when you talk about your uReplicator manager, you said, in your uReplicator manager, you said there's a assignment from route and topic, and where is it persisted? And then
so it's all between manager and the controller, and between manager and the worker, we are still using Helix. So
is it one of those Helix clusters per route, or a separate central?
A separate Helix.
So there's a central Helix cluster used by the manager as well.
Not yeah, more like that. So we have a like Helix here, Helix class here, but between the manager and the worker, we will have another Helix.
I see. Okay.